Hello class, welcome to Geology 12. I'm going to continue my lectures on oceanography. So remember, the tides are also waves, but they're very long period waves. They range anywhere from 12 hours to 12 hours and 50 minutes per tide crest. Remember, the period is a time between successive tide crests. Because they're influenced, or really they're generated by, remember I talked about disturbing force? The disturbing force for the tides is gravity, and it's really the gravitational attraction between the Earth and the moon, which is stronger than that between the Earth and the sun, because the moon is so much more closer. So again, the other big part of tides is that they're shallow water waves. Because their wavelength is so long, right? So in this case, the wavelength is about 20,000 kilometers, half the circumference of Earth, right? Earth is about 40,000 kilometers. Then that would mean that the ocean would have to be deeper than 10,000 kilometers in order for it to be a deep water wave, right? Because remember, the wave base is the wavelength lambda here divided by 2, or half the wavelength. On average, the ocean is about maybe 4,500 meters deep, not 10,000. So there has to be a shallow water wave. So the whole seafloor is moving and there's friction on the seafloor. The other part that I'll discuss here is about gravity. And so remember, the force, the disturbing force is gravitational attraction. And the formula is the force equals this gravitational constant, which is universal. You can measure it anywhere on Earth, on the moon, on Venus, on Mars, and it's going to be the same number. The only thing that's going to vary here are the masses, the mass of body 1, in this case like the Earth, and the moon, mass 2. But the key thing is this denominator here, the distance between the two objects squared, right? So this is really important. So the farther objects are, the bigger this denominator gets, the smaller the gravitational force, right? So that's why the sun has about half the gravitational force on Earth than the moon, because the sun is so much more farther away from Earth than the moon. The moon is only about 385,000 kilometers away. The sun is 150 million kilometers away, so it's much farther away. We need to start thinking of the Earth and the moon as one system spinning around in space about each other. And you'll see that gravity works toward the center of mass. There's always a center of mass here. And so the gravitational forces will always be attracted to that center of mass. So in this case, there must be a center of mass of this Earth-Moon system. And that center of mass is called the barycenter. I want you to know this barycenter. And the barycenter occurs about 1,600, 1,650 kilometers within inside of Earth, because Earth is bigger, right? So it's like the balancing point between the center of mass of Earth and the center of mass of the moon over here. Kind of the analogy they have down here is you got this wrench, right? And it's kind of spinning around together as it goes along this path here, like this orbital path around the sun. And so this Earth-Moon system is spinning about that center of mass. And so that's what the Earth-Moon system is doing over here. It's spinning about this barycenter, which means that there's going to be some inertia, some force driving water away in the opposite direction of the Earth, from the moon, right? So we're going to get a lunar bulge that occurs, and it's really due to inertia or centrifugal force that's going to be on the side of Earth opposite the moon. But since we have gravitational forces, there's going to be another lunar bulge that's going to be attracted toward the moon here. In fact, I have a little cartoon that I've been working on here. I call it the equilibrium theory of tides. So let's zoom in on this. And I've already kind of made some points here, and I'll point different things out as we go along here. You see that on Earth, I got the Earth here and the moon over here. So I got the center of mass of the moon here. This would be the center of mass of the Earth here. And you'll see that there's this point called Z, and that Z is called the zenith. So that's a point on Earth closest to the moon, so it's going to have the strongest gravitational attraction. And then I have these vectors, these arrows. So a vector, the key thing about a vector, it shows strength and direction. Strength and direction is the key thing. So relative strength in our case, right? So you can see I have the vectors drawn longer at the zenith, right? So in other words, there's more gravitational force there. But then at this letter N over here, that's called the nadir or nadir, N-A-D-I-R. That nadir is a point on Earth farthest from the moon, which means it's going to have the weakest gravitational vector, or the smallest strength, right? So in other words, the gravitational vectors vary. They're weaker on the side farthest from the moon, stronger on the sides closer to the moon. So you can sort of see them here. So the zenith and the nadir. So you can see the vectors over here are smaller. They get bigger at the center of mass of Earth, and they're the biggest at the zenith, right? The other thing to notice is that these vectors all point toward the center of mass. In other words, the gravitational vectors are not parallel. That's one thing that I meant. They're not parallel because they all converge to that center of mass of the moon. Right, so the reason, and then the other type of vector is because Earth and the moon are spinning around about that barycenter, right? We're going to get this inertia bulge or centrifugal bulge on the opposite side of Earth. You'll see that every point on Earth is going to spin the same diameter. It's going to spin the same diameter. No point on Earth is different because it's a whole planet and moon system that is spinning around that barycenter, right? And so that means that every vector, every force, every inertia vector or centrifugal vector is going to be the same distance, the same strength, right? Same strength. And they're going to be parallel to each other. So that's another important point, is that these inertia vectors or centrifugal vectors are parallel to each other. So I drew them in red here. So you can see this one here, and they're all the same relative strength, right? Same strength, same direction. So what I want you to see as we're working on this diagram is that the gravitational vectors on this lunar bulge side are larger or stronger than the centrifugal vectors. Whereas on this side, the centrifugal vectors are going to be larger or stronger than the gravity vectors, right? And so you get this centrifugal bulge, right? Or inertia bulge on this side, right? So that's really what's kind of pulling and pushing the water. In fact, there's another, I talk about these tractive forces down here. So the tractive forces are gonna push and pull, got these arrows going here, are pulling or pushing the water into these tidal bulges, right? That's a key thing. They're pulling or pushing the waters into these tidal bulges, right? So as we go over here, there's the result is we're seeing that lunar bulge and that centrifugal bulge, and then the result is we get the two bulges, right? So there's always going to be two, one due to inertia or this centrifugal spinning, right, around the barycenter, and then the gravitational bulge over here, right? So gravitational bulge or lunar bulge is what I call it. There's a centrifugal bulge over here as well, right? And then you see the combined effects there. And then as we go back over here, I'm talking about this equilibrium theory of tides. And it's really simple, and it's kind of an elegant way to present it because it's got simple vectors and you can relate to the forces. But really, it doesn't exactly work like this on Earth because we have continents. So the whole thing about this equilibrium theory of tides is that it assumes there are no continental land masses that will impede or alter the flow of the tide crest as Earth is spinning, right? So, but we do have continents, and so there is a dynamic theory of tide, which is a little bit more complicated. I'm really not going to get into that because it's going to involve a lot of other mathematical equations. But for now, this is a really simple way of understanding how tides work, because really the key is, and I wrote it down here, the key to the equilibrium theory of tides here is that Earth spins beneath the tidal bulges. Earth spins beneath the tidal bulges. So in other words, here I have Earth's axis, North Pole, South Pole, and you can see it's going to have an eastward rotation. So Earth is spinning eastward, right? Spinning eastward around this axis. And so at this point, you know, if there's an island here, this island would be, here I have the word trough. So remember the bulges would be the crest of a wave, right? So that'd be like the crest up here, and the trough would be down here. So currently this island is at low tide because it's at a trough, right? It's at a trough. But then as Earth spins 6 hours later, this island is going to be over here, right? And it's going to be under a tide bulge. So it's going to be at high tide. And then 6 hours later, it's going to be back. Remember, back on the other side of Earth over here would be another trough back behind Earth. So it'll be low tide. And then as Earth spins again, the island will be out over here, right? And it'll be under another high tide. So you'll see 2 high tides per day, 2 low tides, right? The one on the opposite side of the Earth. So that's the key, is that the Earth spins under the tide bulges, right? And I'll talk here about the lunar day and the solar day in the next slide here. So the moon is also moving, right? But it's moving much more slowly around Earth than Earth is spinning. Because remember, Earth spins in 24 hours, right? It does one revolution or one rotation in 24 hours. But it takes the moon almost 30 days to orbit the Earth, right? And so you can see here that if you start at one point here where you're at a tide crest there, the moon is directly over your position, you'll spin over the course of 24 hours, you'll do one revolution, you'll come back to your original place, but the moon also moved a little ways, right? So you would have to move an additional 50 minutes to be at that tide bulge and the moon directly over your meridian, over your longitude, right? So that's why we say a lunar day is 24 hours and 50 minutes, whereas a solar day is 24 hours, right? And so the moon rises 50 minutes later each day, so the greatest tidal influence at your meridian, at your longitude, occurs 50 minutes later each day. So that's why the tides are changing, right? They're coming in at different times because, well, actually, it's really because of the land masses, the dynamic theory. But really, the underlying change is really this lunar day here, 24 hours, 50 minutes. And then I mentioned something how the Earth is much closer to the moon than it is to the sun. So it's 385,000 kilometers to the moon, 150 million kilometers to the sun, right? So remember that denominator, it gets really huge for the gravitational forces with the sun. So it's a weaker force. But the key number I want you to know is down here, is that the sun's gravitational attraction on Earth's ocean is only 46% that of the moon. So about half. I just say about half to make it simple, right? And then the other part we want to discuss here is this idea of spring tides and neap tides. So spring tides have nothing to do with spring. Spring tides occur in the winter, in the fall, in the summer, and even in the spring, right? It really has to do with kind of springier or more or higher, right? So they're going to be higher high tides and lower low tides. So these spring tides are occurring when the Earth, Moon, and Sun are on the same geometric plane, for example. And that would be when we have a new moon or a full moon, right? New moon. And so you can see that there's an addition or an additive effect between the tidal bulges. Because the sun also has a tide bulge, right? It's going to be about half the size of the moon's, right? Because it's about 46%, right? But when they combine, when the two crests of the wave combine, you get they call it a constructive wave interference. So you make higher high tides, and then by the same token, you would have a lower low tide. Remember, the trough would be here. So spring tides occur during the full moon and the new moon, and then at the quarter moons, whether third quarter or first quarter moon, note that the geometry is a 90-degree angle. So in this case, the trough of the lunar tide coincides with the crest of the solar tide. So you get a subtractive effect where the trough of the solar tide will take away some of the height of the lunar crest here. So you get lower high tides and higher low tides. So let's say that again. So during the spring tide, you'll see higher high tides and lower low tides. In fact, that's what we're going to Natural Bridges next week, because it's a spring tide and we're going to go during a time of low tide. And we want it to be a really low tide so we can go down and see the tide pools, right? Now for the neap tides, here you're going to see lower high tides but higher low tides, right? So think about that. It should make sense. But again, spring tides, full moon, new moon, neap tides, quarter moons, right? Okay, well, let's stop here for now.